All right, this is problem number 2 from practice exam 3-1 in the fall 2021 semester in Chem 1211. And the problem presents us with this, which is an orbital energy diagram for the hydrogen atom. Problem mentions the hydrogen atom and asks us about the wavelength of the transition indicated by this upward pointing arrow. Now, what are we looking at here? Let's take a step back, take a breath. What am I looking at? I'm looking at the energy levels of the hydrogen atom. These are principal quantum numbers starting at n equals 1 and moving up to n equals infinity, where the electron is an infinite distance from the nucleus. So as I move up, the electron, or the atom itself, is going up in energy. And of course, the gap between the horizontal lines represents an energy difference between two levels and potentially a transition between those two levels. So this upward pointing arrow is indicating a transition from n equals 2 to n equals 4. And broadly speaking, what we're dealing with here is the Bohr model of the atom. This picture of the hydrogen atom that posits that it is composed of a series of orbits at discrete distances from the nucleus, with each discrete step outward modeled by an increasingly large n value, where n goes from 1 to 2 to 3, etc. So the transition of interest here is from n equals 2, that's the lower level, to n equals 4. Now, before getting into the nitty-gritty of determining the wavelength associated with this transition and what that means, let's talk about whether this represents absorption or emission. The electron is going from closer to the nucleus to farther away. The electron, or the atom, is going up in energy. So what's happening here, essentially, is the hydrogen atom is gaining or absorbing the energy of a photon to produce a hydrogen atom in an excited state. And what happened to the photon? Well, it disappeared because it was absorbed by the hydrogen atom. This is absorption. And I know that because the transition is upward in energy. The photon is absorbed, and this is what provides the energy for the transition from n equals 2 to n equals 4. This is what allows us to bridge this gap. The other important thing we get out of that analysis is the energy gap right here corresponds to the energy of the photon that is absorbed. And if we can figure out that energy gap using some kind of equation, for example, we are able to figure out the energy of the associated photon and its associated wavelength. So let's think about that photon for 1 second and notice that its energy is going to be related to its wavelength using h times c divided by lambda. So the wavelength is inversely related to that energy. And again, if we can figure out the energy through some kind of equation, or even the wavelength directly, we can figure out the energy of that photon. So how do we do that? Well, we've got to somehow engage an equation that relates these n values and the difference between an initial and final n value in a transition to a wavelength or an energy. And what pops into my mind is the Rydberg equation. Of course, the Rydberg equation and Bohr model are deeply related. And I'd say the Rydberg equation is one that you're definitely going to want to have on your crib sheet. So the Rydberg equation says, for example, that 1 over lambda is equal to a constant, which we call the Rydberg constant, or R infinity, times, now for an absorptive transition, this is going to be 1 over the initial value squared, 1 over 2 squared, minus 1 over 4 squared. And just to make this a little bit clearer, this is our initial n value in initial, and this is our final n value. And here I'm assuming that the Rydberg constant is greater than 0, so that this whole right-hand side becomes greater than 0, and 1 over the wavelength, of course, must be greater than 0. So the Rydberg constant, normally in the problem, it would be provided. For the purposes of solving here, I'm just going to pop right into Wolfram alpha, plug it in, get the answer. Rydberg constant times 1 over 2 squared minus 1 over 4 squared. And we can actually invert this whole thing, or raise this whole thing to the -1 power, or do 1 over this whole thing. And this entire expression should have units that are equivalent to length, right? Equivalent to wavelength. Since 1 over lambda equals the Rydberg constant times this difference, 1 over that will pop out lambda. So let's try this in nanometers, since that's, after all, what's listed in the problem. And there it is, and the value is 486 nanometers. So you'd have to do a bit of algebra to solve this on your calculator. The Rydberg constant would be given, but the Rydberg equation is something you'd want to have on your crib sheet. So 486, there it is, 486 nanometers, and that should be one of the choices. Let's make sure that it is. Yep, 486 nanometers absorption. There you go.